Okay, this is problem 1115C. It's on page 630. Figure P1115 shows a beam supported at its ends by pin joints. The inclined bar at the top supports the right end of the beam, but also places an axial compressive force in the beam. Would a standard S150 by 18.6, which is an S6 by 12.5, beam be satisfactory in this application if it carries 1320 kilograms at its end? The beam is made from ASTM A36 steel. Well, let's jot down what we've got. It's A36 steel. And let's start off by solving the statics part. So the sketch, the figure's on page 631. A sketch of the figure looks like this. There's a pin joint here with a member that comes down to another pin joint here. There's a pin joint to the wall of the beam. Now the beam we're interested in is this one, because there's a load out here. Now why do you think it's this beam we're interested in? Why are we not interested in the top one? The top one's in tension, right? This one's not going to fail by buckling. It's the bottom one's going to fail by buckling. Hopefully your intuition is strong enough you can see that that's in compression. Okay. So let's just go ahead and solve this with statics. How would we solve this with statics? Do you know? Well, it's pretty simple. If you were to look at the load in this upper member, the load would be directed along the length of the beam, right? Because it's pin to pin. So you know the direction of the load has to be like this in the beam. But the applied load has to have an equal and opposite vertical force. Ignore the beam for a second. You have to have something equal and opposite in this direction. So basically what that means is that, here, instead of using load everywhere, let's use the numbers. So what, 1350 kilogram load, or 1320? Well, that's not a load, that's a mass. So calculate the weight if you would. 1320 kilograms times 19 or 9.81 meters per second squared is how many newtons? It's about 13,000.
12,949.
12,949? Okay. So that would be newtons. That's how big this has to be, right? 12,949 newtons. And so basically geometry would give you the magnitude of this side, which is what we really want. No, it's not what we want. But that would give you the load. Now, what does that mean? Well, the other piece of this piece has to be supported by compression in this member. Basically what we're doing is a free body diagram of that pin. Okay, that's all we're really doing. We're saying if you look at that pin, you've got the applied load of, can I just call that 13 kN, just to make it simple? There's a load in that direction and a load in this direction. This is the piece we want. And so basically you can extract a force triangle from that, which is basically this right here, and figure out the magnitude of this side. So the easiest way to do this, in my opinion, is just to use the fact that this distance is 1 meter. This distance, that arrow. This distance is 2.4 meters. So what does that tell you about the relationship between these two loads? 1 to 2.4, right? So all you have to do to figure out the magnitude of the compressive load in the lower beam is to take the 12,949 newtons and multiply it by 2.4 over 1.0. Okay? That's the quick version of how you do this. Basically, all the forces on this pin sum to 0, therefore they create a force triangle. Okay? So I won't go through all the gory details of the statics because I know that's what our result will be. So just take the 12,949 you still have in your calculator, multiply it by 2.4, and you will have the magnitude of the compressive load in the beam. And that's the piece we really care about. So what's the result? It's going to be 26,
31,177.
So the load that we're interested in, let me just call it P, and then we can get rid of all this extra junk. The load we're actually interested in on the beam is a load of, you said 31,000, how much?
77.6.
77.6. Oh,
31,000.
77. Okay. So let me just jot this down. We don't need the figure anymore, right? Okay, there's the compressive load on the beam. Now, how is that beam fixed on its end? Or what's the end conditions of that beam? It's pin, right? Both ends are pinned. I see discussions. Any questions so far? So both ends, so basically all we have to do is analyze a beam that looks like this. Where we're applying a load of 31,077 newtons. Now, what failure theory are we going to use? Are we going to go and use the initial stuff that I taught you, the first principle stuff? Remember, this is a steel beam, right? It's a particular cross section. So I think we should use AISC's recommendations in order to solve this problem. So let's go back and see what they had and how they told us to do it. Let's see, page 621. Remember, they also use the slenderness ratio. So we should probably calculate the slenderness ratio for this beam. And that was the effective length divided by the minimum radius of gyration. Okay? So we need to go get those things. Well, how long is this beam? It's 2.4 meters long. And since the ends are both pinned, then what is the effective length? You guys remember? Where would you find it? One of those factors, isn't it? It's 1.0 times L, page 607. So go to page 607, please, and you'll see the effective length. You have to choose from one of those four options. So it's pinned, so pinned end columns. Means the effective length is just 1.0 times the length. So calculate this, it'll be 2.4 meters divided by whatever the minimum radius of gyration happens to be. Where will we find the minimum radius of gyration? In the back of the book, right? Because this is a steel column, so what we'll have to do is go back. This is an S shape. Find the S shape, so that's page 702, 703. Which one do we prefer, 702 or 703? 703, that's right. Why? Metric. It's metric. We're dealing in metric in this problem. So it's an S150 by 18.6. Looks like that's reference line Q. So page 703, reference Q. What do we need? Well, we need the minimum radius of gyration. Did they give us that? No. So how are we going to calculate it? Okay. So what I should we put in here? Should we put in IY or IX? IY because it's the smaller one. Good. Okay, so on Q, looks like IY is 7.49 e to the fifth. That's the same thing as saying times 10 to the fifth. What are the units of I? Millimeters to the fourth. Good. How about the cross-sectional area? Does that matter which axis we choose? It's just a cross-sectional property, right? Okay, so Q, what is the cross-sectional area? Anybody see it?
2,360.
2360, good. And that has units of millimeters squared. So what will our radius of gyration number come out in? Well, units. Millimeters or millimeters squared?
Millimeters.
Millimeters. Don't forget you got to take the square root. So millimeters squared cancel with two of these. Let me do it this way. So then if we take the millimeters outside of the square root, we'll just have millimeters. So plug that into your calculator, please. 7.49 e to the fifth over 2360. Don't forget then to take the square root.
17.81.
17.81. Okay. Which, do I want it that way? Well, I'd like to have it in meters, right? So all I have to do is move this over three places. We'll just plug it. 0.01781 meters. Notice the slenderness ratio is dimensionless. It should always be dimensionless. It's a ratio of two lengths. Okay? And it looks like I got that right. So take the number you've got, divide it by 1,000, invert it, and multiply by 2.4. See what you get. have a number?
134.7.
134.7, anyone second that? Thanks. So, one thing you should do when you have a non-dimensional number is put ND behind it to make it clear that you know you're talking about a number that is dimensionless. ND means non-dimensional, okay? So 134.7 is our slenderness ratio. Great, what do we do with that? Well, we go back to page 621 and calculate the transition slenderness ratio. So we'll use equation 11A. SR sub T is equal to 4.71 root E over SY, the yield strength. So let's see, 4.71 root, the elastic modulus for steel, I've got it in PSI, but not in gigapascals. I think it's 309, but maybe not. Nope, it's 207. If we go to page 714, look up typical properties of carbon and alloy steels, 207 gigapascals is a good number for the elastic modulus. Now, the elastic modulus does vary a little bit. Let's see, on the structural steels, do they have? No, they don't. I was going to see if in the structural steels they have, oh yeah, they do. They've got a different number. Page 717. The American, this is the properties of structural steel. Since we have a structural steel, it makes sense to go there. We have what, A36? Yeah. Okay, so it looks like at the bottom of this table, they recommend 200 gigapascals instead, so we'll go with that. Not much difference than 207, but we'll be as accurate as possible. Okay. How about the yield strength for A36? Do you guys see it on page 717? See yield strength for A36? Page 717. It's at the very top.
248.
248, that's right. 248 what? Megapascals. Okay. Can we just plug this in our calculator? Is that okay? No, we've got a problem. See what happens when you don't use units? You get messed up. Watch. These were gigapascals. These were megapascals. They're not the same. Being $1 billion in debt is a very different situation from being $1 million in debt, right? I wouldn't want either one, but one is worse than the other, okay? Being $1 trillion in debt is ludicrous, so what does that tell us about America? Anyway. So, how do we resolve this? What do we need to do? Well, why don't we just add 3 zeros? That's what the politicians say, right? Just add 3 zeros. Now we're in megapascals. So 200,000 megapascals divided by 248 megapascals, and then square root times 4.71 gives us what?
I got 133.76.
Anyone second that? 133.76, so 0.8 or so? Anyone agree? I do. Okay, thank you. All right, now. The elastic critical buckling stress, we'll just continue down through equation 11.9, although we could jump to 11.10. We're going to need 11.9 anyway. But let's go ahead and, let's see, it's also called the Euler stress. Let's go ahead and calculate SE first. It is pi squared E divided by the slenderness ratio squared. So this would be pi squared multiplied by 200,000 megapascals divided by a slenderness ratio of 134.7 squared. Plug that into your calculator, please. And let's find out the elastic critical buckling stress. I have to get used to these names and these terms.
Is it 134.7 or 133.7?
134.7 because we're using the slenderness ratio, right? This is the transition. This is what determines whether we've got a long column or a short column. All right.
108.8.
108.8? Okay, and that would be megapascals. We're gonna use this in a little bit, but now we get to compare these two. Which one's bigger? Slenderness ratio, right? So this is slightly below this, or another way of looking at it is this is slightly above this. This is kind of like the speed limit, right? Above this, you go one way, below it, you go another, okay? This is the cutoff ratio, really, is what that is. Anyway, look at equation 1110. If the slenderness ratio is less than the transition slenderness ratio, which is not the case, then you have a short column, and that's equation 1110. Notice it's really close, and we could potentially calculate it. We won't, because it's apparently not a short column, it's apparently long. Next page, 622. If the slenderness ratio is greater than the transition slenderness ratio, which is the case, right? In our particular case, we know that SR is greater than SRT, the transition. Then what that means is we have a long column, and we have to choose equation 1111. So that looks like this. The critical stress is about 87.7% of what they call SE, the Euler stress, the elastic critical buckling stress. Okay, so SCR would be 0.877 times SE. So if you take 0.877 times 108.8 megapascals, what do you get?
95.4.
Thank you. 95.4 megapascals, that sounds right. Okay. So then what? Well, we're supposed to compare this somehow to this load, right? This is the critical stress, but that's how much load's actually applied. So what do? Well, we look and see how much cross-sectional area there is. All of that cross-sectional area will have this stress, right? This is simple direct compression is all it is. What kind of stress will this beam experience? Normal stress, right? So normal stress, not shear stress, but normal stress. Okay, so there's SCR. In order to calculate the critical load, what we have to do is take the critical stress, multiply it by the, what do they say, G is the gross area. Where are we going to get the gross area? Back to the book. Well, we already got it before. Unfortunately, I've erased it. Okay, so we'll have to go back and find it again. Let's see, so what was that, page 703, I think? Yeah, 703.
2360.
2360, thank you, that's right. So 95.4 megapascals times 2360, and that was millimeters squared, right?
Yeah.
Okay, well, remember that if we take gigapascals times millimeters squared, we'll end up with kilonewtons, right? So it'd be more convenient to have this in gigapascals. So let's put it into gigapascals. How's that? I just moved the decimal place over 3. Okay, so take 0.0954 times 2360, and our result will be kilonewtons. Anyone have it? 225.2 kilonewtons. Hey, looks like we're doing okay, are we? Remember, they have a factor of safety they recommend. How much factor of safety do they want? They said use 1.67, didn't they? They said that the allowable load would be equal to the critical load divided by 1.67. They don't want to use the full capacity of the material. So take the number, if you still got it in your calculator, it's 225.2 kilonewtons, and divide it by 1.67. 134.8 or so, and that would be kilonewtons. That is more than 31 kilonewtons, so yes, it's safe. Does that make sense? Any questions? Because the allowable load is more than the applied load, everything should be all right. No questions? All right.